you're writing to submit it somewhere? You know what?
Hi, good morning, everybody. So I'm pleased to welcome Pierre Gaillard from INRIA Paris for introducing this day, which will be about online forecasting and specifically aggregating forecasts. So it's a specific topic on forecasting, but very general, and that could be applied to a lot of forecasting problems, as we experience recently. It is a work following years of research we did with Pierre and Gilles Stolz from Université Paris Sud. We did that during the PhD, and now it's in use at EDF for operational forecast at the national level.
Thank you, Yannick. So I guess Yannick explains what I will be talking about. So in a few words, the goal in this application was to forecast the electricity production in France, so the global electricity production from EDF customers, and 1 day ahead, so in short term. And well, I guess it's you know all about this, but it's important because it's hard to store electricity in large scale, and so you always need to adapt the production to the demands, and so to have good forecast of the electricity production. And since it is an important problem for EDF, they worked on it during years, like during the last 30 years, and they have built like many very good forecasting models for electricity. For instance, some are based on splines, like GAM, a specialty from EDF. Some are like autoregressive models. Some are like models on curves, models based on similarity, like k-nearest neighbors, but on curves, like to forecast the next day according to what are the days in the past that are looking as today. And some like there was some work about machine learning models like random forest, deep learning, and historical models with people trying to fit directly with experience. And the question is, okay, we have all these models, and the question I wanted to answer during my PhD was, okay, which one is good, which one should we select? And instead of selecting one of these models, we decided, okay, we will combine them. We will assign weights to each of the models, and then predict like a weighted combination or weighted average of the predict forecasts of the different models. And so the question is how to assign the weights, and how to choose the weights, and how to adapt the weights according to the changes in time, and how to make them evolve. And why did we want such kind of model? One of the reasons is like, okay, maybe some model is not was good like during the last 10 years, but there are some changes in the stage, like with electric cars, energy bulbs. I guess you know all of that very well. Like changes in the production with more and more renewables energy, changes in, like political changes with the opening to competition of the French electricity market, for instance. And so, because all of these changes, like maybe the models that were good 10 years ago or 5 years ago will not be the best one tomorrow, and we have to find some methods to combine the model, but that adapt to these changes, that evolve over time and adapt automatically. And the next question, before deciding how to choose the weights, was what assumption did we decide to make on the data? Like, do we decide it to be IRD? Do we decide it to be an autoregressive model? And one of the difficulties we had to face was, okay, but we want to combine all these models, but each model is making a different assumption. So, like, if we use some random forest, it assumes some stochasticity, like ID data. If we use autoregressive models, it assumes like time series. It has some time series assumption. And how could we combine all these models that each of them had like a different assumption, and so we decided on the aggregation part and the combination part to make no assumption. So if we combine the model without any assumption on the data, using like some kind of game theoretical point of view, like maybe we will be as good as any model in its assumption. Like we won't make it. This is the only way we found to combine the models that were very different. It was really hard to unify this into a common framework. And so there is a setting for this, and it's the setting of prediction of individual sequences, of arbitrary sequences. And there is a good book, a good reference for these types of problems. So it's quite theoretical. I guess you won't see any application in energy, but it's like prediction, learning, and games. And so now we can move to the framework. So the framework is the following. So each day we want to forecast the electricity consumption of the next day. We know the electricity consumption of the previous day. And before making our prediction, our forecast, some experts, like some methods, like for instance here we have 3 methods that produce some forecasts. And we see them. We assign a weight to each of these forecasts, and we predict a weighted average of the forecasts before seeing like the next turning on to the next day. And it's like a sequential problem. Like we move from one day to another, and more we will see more data and trying to learn the weight sequentially, like on the run. And we make no assumption on the white curve, like on the there is no assumption on the white curve, and there is no assumption on the models. Like we assume that it's like all of them can be chosen and can be picked by some adversary. And now we need before choosing the weight, we need to decide about the performance. What are good weights and what are bad weights? And the weights are updated every day according to past performance. And one thing which is important to understand is like okay, garbage in, garbage out. Like it's some kind of principle in machine learning. I mean, if all models or all experts that are provided by EDF are garbage or very bad, there is no. It's impossible that the combination method will give an accurate forecast. So it's not possible to have like we need a relative criterion. It's not possible to have an absolute criterion and our loss, but we do like a relative criterion, and the goal will be that our average performance. So if you consider the square loss, the difference between our prediction with a hat, so with a hat it's our prediction, and the true electricity consumption in average, we ask it to converge as on the long run, as the time goes to infinity, to the average loss of the best model. So xkt is the prediction at time t of model k, and so we want that at least our average performance is at least as good on the long run as the best of the models. So we don't know it in advance. We don't know in advance which one is the best model, but we want to converge to it. And so if all the models are really bad, our average performance will be really bad. But if it appears that some of them is good enough, we will have like a good performance. And we want it to be true for all possible data. So for all possible yt and all possible xt. So for any prediction of the models and for any electricity consumption, because we didn't make any assumption. So this is the goal. And the application, as I told you, was the electricity consumption in France. So the data set we considered was some EDF data sets. I guess now it's a bit old because it was during my PhD. But it was a data set from 2008 to 2012. And it was considering all EDF customers during roughly 2000 days. And we removed uncommoners. And the data looks like this. So I guess you know all this. This is like this is 5 years of electricity consumption in France. So you see that like during the summers we consume less, and there is something which is typical in France is like during summer vacation there is like a really drop of consumption. So it's really French data. And during winter we consume more. Here it's like the relation between the electricity consumption and the temperature. Here it's like the electricity consumption during 1 week. Like during the weekends, people consume less than during the week. And in orange, it's like what we try to predict. So it's not really a trend set and a test set, but we use like 4 years of data to build to train the models. And the last year we will use it to combine them online. So all the performance will be recorded on the last year, but the last year of data will be rebuilt to the combination methods regularly, day by day, to make the forecast sequential. And we used 3 types of models to build the experts. It was like 3 models that had like very good forecasting performance at EDF. The first one is GAM, like generalized additive models. The second one is curved linear regression, which is some kind of regression on curves, I guess. And the last one is some kind of k-nearest neighbors approach on wavelet basis. I won't, the goal is not to explain these models in detail. So the performance we looked at was like the RMSE, so like the square root of the cumulative. There is the 1/t which is missing of the average loss, square root, and the absolute loss. What is important is like here it's like some kind of percentage of error, and this one is like the larger it is, the worse it is. And so before showing the performance of the experts, we will show the performance of some baseline, like the performance of the uniform average of these 3 experts. We got the RMSE of order 700 megawatts, which is roughly 1%, 0.18 of error. And the best of the 3 models gets 1.29% of error. So already doing like a uniform average of the experts, of the models, is already doing better than the best of the models. So even not optimizing the weights or not optimizing them, it's already good to do some average. And we see that this is an oracle, so we don't know it in advance. But if we knew in advance what would be the best combination of experts, like and if we use this combination of models, this fixed combination of models all the way during the test sets in advance, we would do 1.6% of error.
You do your best combination with some least square feet of the weight a posteriori? Or?
Yeah, exactly. So this is cheating. This is
sure.
This one is cheating in the sense that this is the performance we can hope to reach. So it's like to have an idea about what we could achieve doing a combination, expert combination. So these are called oracles. Yeah, it's just a fit a posteriori. And the algorithm we consider to choose the weights is really simple. It's the following. It's just doing like it has some parameter eta, some kind of learning rate, and it's just assigning to each expert. So at time t to an expert k, it is assigning like a weight which is exponentially decreasing in the cumulative error that the expert k has suffered until time t minus 1. So we looked at the cumulative error the experts incurred in the past, and we assign a weight which is exponentially decreasing in it. So it's some kind of and this is like some kind of inverse temperature. And then there is a renormalization so that the weights are positive and sent to 1. And so the worst a model was in the past, the smaller will be the weights that we will assign to it. And the learning rate eta will manage the speed or the rate at which we will learn, in the sense that if we use like a learning rate eta which is 0, then the model will not learn at all, and it will always assign like uniform weights among the experts. And if you choose a learning rate eta which is infinite, then the weight will assign a weight, the algorithm will assign a weight 1 to the expert which was the best so far, and 0 to all other experts. So, and there are some theoretical guarantees, which is the following: like if we are using this kind of weights, well, this algorithm dates from the 90s, and if you are using this kind of weights, then we can show. I guess we can show something better for the square loss, but if we had, we can show this, which is our average error minus the average error of the best of the experts will be smaller than something which depends on eta. And if we optimize, if we choose eta, like the learning rate in a good way, this will be smaller than square root of log k over t. So t is the number of time steps. So our average error will converge to the average error of the best experts at a rate 1 over square root of t. And the more experts we have, the slower will be this rate, but it will be just a dependence. The dependence on the expert is square root of log k, which is like growing very slowly.
So, I mean,
yeah,
the more experts you have, the better you should be. But of course, it's the comparison.
Yeah, this is like some kind of trade-off between, okay, the more experts you have, like maybe the better this term will be, because you might have more chance to have like a good expert. But the more difficult it will be to find these good experts and to fit it online.
And if you don't know capital T, how would you choose eta?
Okay, yeah. Eta is the best value of eta depends on capital T and B. B is a bound on the data. B is like an upper bound on the. If you don't know capital T, there are many ways. Actually, I will talk about it later.
Can I ask you something also?
Yeah.
Wouldn't we be interested in not having S equal to 1 if we, I mean, if the
S?
process in your sum up there for your weighting up there, pirate, yeah. I mean, if the optimal weighting is non-stationary, we don't want.
Yeah, like you're using some kind of sliding windows or using a distance weight. I will talk about that later. This is a proof, so I don't want to explain it or to go into it in details, but what I want to show you is like it's just one slide, so it's an easy proof. And it's using Hövding inequality, which is like some kind of concentration inequality, well-done in probability. And so now I'm answering about the calibration of eta, like the learning rates. So the best value theoretically for the learning rate is this one, so square root of log k over t.
So just about that, so you derived it by optimizing the bound? Or?
Yeah.
Oh, okay.
Yeah, it's just we optimize the bound because when we are doing the analysis, we find like a competition between two terms. One is with 1 over eta, and the other one is plus eta. So this one is going larger with eta, and this one is when eta is increasing with eta. This one is decreasing with eta, and so we can optimize it. And so there are several ways to if t and b are not known in advance. And one is known as the doubling trick. And so the doubling trick is like every time the time is of the form 2 to the I, like at time 2, at time 4, at time 8, we restart the algorithm with a value of eta which is divided by 2, or something like that, or divided by square root of 2. So there are like but this is good in theory and very bad in practice because we restart regularly the algorithm, forgetting everything in the past. So it's like it's not. But in theory, we don't lose anything except a constant factor. There are some other solution which is just replacing the big T by a small t, by like the current value of the time. And a last solution, which is maybe the best in practice, is running some different algorithm, different copies of the algorithm with different values on eta chosen on the grade, and then doing some choosing addition doing the best of them, like the one which was the best in the past. Like, and if you are doing this, you see that the values of eta at the beginning it's like moving a little bit, and then it stabilizes. But normally, in theory, it should decrease like in a rate 1 over square root of t. So now is the performance that we get using this kind of way. So these are the benchmark. Remember? Oh, it's fun because it's not. Yeah, it's the same. It's the same. But I told you in percentage. But here it's in MES, and we see that the algorithm, if we use the best value of eta in theory, is doing better than uniform, but a bit worse than the best weight in advance. But if we tune eta better, we get like performance that are like getting close or even that are even better than the best combination posteriori. And these are like okay. Here we have only 3 experts, so it's like quite easy to combine them. So the 3 experts that I told you, there is one light blue, one orange, and one dark blue. And here we see the evolution of the weights according to time. So there was roughly 1 year of online optimization of the weights. So this is time, and this is like the 3 weights that are summing to 1. This is why the sum is always 1. And we see that one of the experts of the models is getting like a weight which is enlarging, and the other one is getting smaller. But actually, this is, I think we should have done this graph during 2 years, because if we did 2 years, we would see that actually the light blue expert would have a weight which would increase again, like in September or October, because the light blue expert is better during winter period and worse during summer period, and so there is like some kind of pattern which is evolving. So this was not the purpose of the graph. And these are like using the exponential weights in theory, and this is like using the same algorithm but with the like a more practical calibration of the learning rate, and we see that we get an algorithm which is much more aggressive, which has like weights that are changing much more rapidly than the one in theory. And the reason is like the learning rate which is chosen in theory is chosen to face adversarial data, like in the worst case data, and so it's like very it's very careful, like it's too careful, like it's like it changes very slowly to face like something with a lot of incertitude. But in real data, in real environment, the data is not adversarial. It's not worst case, and so it's maybe better to have some kind of.
So this is due to the opening or not? Or
what is due to?
The fact that you are in the worst case, like what?
This is due to. Opening is a way to in the proof to face this problem, like it's a technical tool, but it's like an assumption. We assume that we are in the worst case, and we are trying to have like inequalities. These inequalities are just like here you get inequalities that it's just you are doing inequalities without doing any RID assumption or any stochastic assumption. It's like deterministic inequalities. And so one of the questions is like here we see that in this case the light blue experts disappear, and so okay, what would have it been better to just have 2 experts like the dark blue and the orange one? Because the first time I showed these results, there was the name of the experts of these 3 experts on this. And the one who created the light blue was but my model is good, and you should not show that the weight disappear. It's not, and actually it's not even the light blue is not useless. If you use just these 2 experts and we combine only these 2 experts, we get worse performance than if we combine the 3 experts. And the reason is like the light blue expert was better during winter and was it was needed, and it was better to include it in the aggregation. Even if the
Can I ask you something?
Yeah.
What about the dependence among experts in this case?
It's square root of log k. So square root of log. So it's like very very small.
What I was meaning, if we have, let's say we have n experts, with n getting quite large,
Yeah.
but we have n minus 1 experts that are very bad, and 1 that is very good. All of these bad experts are highly correlated, and they all get a small weight,
Yeah.
but somehow they all add up in terms of weight in the overall aggregation, right?
Yeah, but since the weights decrease exponentially fast, theoretically it will only appear as a square root of log n. So it should stay good. But there are, in this case, there are better algorithms than this one. If we assume that one expert is much better than the other one, or if we assume that many experts have the same performance, there are other algorithms that have better performance. Yeah, I'm just showing like the most famous one. Okay, now is what you asked about the time adaptive methods. So okay. In the application that we showed, I told you that the light blue expert was better during winter and worse during summer. And so maybe it's not a good idea to compare with fixed experts, assuming like the best experts, which is fixed among all the experiments, that you would like to compare with experts that vary, or models that vary over time. Like some experts that are good during winter and some that becomes better during summer. And instead of comparing with the best fixed expert during the whole data set, we would like to compare with the best sequence of experts that change not too often. And it's possible to do so. And one solution, there are many solutions, and one of the solutions is to use like the same weights as before, like exponentially weighted updates, like the same weight as before, but having like some additional exploration term in alpha that force all of the experts to have like a non-zero weight, like a weight which is far away from zero. So at each time, we still assign a weight alpha divided by k to any of the experts, and we use 1 minus alpha times the exponential update. And we are doing so, none of the experts will have like a weight which will vanish to zero, and if some experts or some model starts becoming good again, it will be able to recover rapidly a large weight, which was not the case with the previous algorithm, because in the previous algorithm, if some model was really bad during a long period, and it starts being good at some points, its weight will just have killed him, because it will have like a weight which will be so close to zero that it will never recover. And with this one, if you choose alpha small enough, but in the right order, I guess we get theoretical guarantees that are of this form. It's like our average error of the algorithm will be smaller than the average error of the best sequence of experts. So instead of comparing with a fixed expert, we compare with a sequence of experts, plus a term in square root of m log k divided by t. So this is order. So log k, square root of log k divided by t is the same as before, but we have like an additional multiplicative factor of order square root of m, which is the number of changes in the sequence. So if in the sequence there are like t changes, we won't be able to adapt to a sequence of experts which is changing all the time. But if the sequence of experts does not change too many often, so less than sublinear amount of time, so if it evolves slowly, we will be able to track it. And in practice, I won't show the experiments because they are similar. In our datasets, the results were similar to the one we got with exponential weights, but you get much more unstable weights because each time some experts start being better, it's like the weight is going to increase, and so I'm not sure EDF likes this algorithm very well because you have like a lot of instability. And there are some other ways to get time adaptive methods. Some are like you can use sliding windows. In the sliding window, instead of summing from 1 to t minus 1, you can have like some kind of window which is slowly going like summing from t t divided by some a sliding window from the end, or you can have like some kind of discount factor that assign more weights to the recent time to recent performance. The issue is like these ways of dealing with time with methods or experts that are varying over time. It works in a stochastic setting like autoregressive or I don't know, stochastic model. But when you are facing with adversarial data, like worst case data, it's really hard to analyze these methods. But it's possible in practice. It works in practice, but because the data are not adversarial, but you don't get theoretical guarantees.
So why is it hard?
But it's hard. It's hard because here if you do like this, you won't get guarantees on your cumulative. Yeah, I don't know. It's hard because in your cumulative performance that you are looking at the ends, you are looking at like the cumulative sum, which with the same weight all over time. And so if you want deterministic inequalities and you have some sliding, some discounting factor, it's really hard to get rid of this, to manage this discounting factor in a smart way with deterministic inequality. I don't know. Well, it's just that we couldn't do the analysis. It's like, but it works in practice. You can do so. And one remark is like until now I told you that we had a method that was converging to the performance of the best expert. But sometimes, as we saw in the experiments, the best expert was not that good. The best expert had like 744 RMSE, while the best combination of experts had an average error which was much better, like 600 or something like that. And so one maybe more ambitious goal would be to have an average performance which converges not to the best experts but to the best combination of experts. And there is like a trick which is like well used in this literature. Is just to change the loss. Like if you have a method where you can ensure that it converges to the best model, you just by changing the loss, like using the gradient trick, instead of using directly the square loss, for instance with the square loss, we use the gradient of the square loss. You can and you put this new loss into the algorithm. You get a method that converges to the best combination of experts. You just have to modify the way the loss you put into the algorithm, and you get guarantees of this kind. And the reason is like, for instance, assume you have like so I don't know which one. Okay, observation. Okay. Yeah, for instance, here for the square loss, we see that so our prediction in blue, expert. Okay. I was looking at. So, for instance, for the square loss, assume you're in this kind of situation where in blue it's our prediction, in red, like in orange, you see like the prediction of some experts, and in gray the observation. You even if the expert was really bad in doing the prediction of the or was quite bad because it was like underestimating the prediction, the true value of the consumption. You want to increase its weight just to increase the weight of the orange bag to make your prediction smaller, to make it go to be closer to the observation. And if it's on the same side of like if you are overestimating the observation and the expert is also overestimating the observation, you want to decrease it, to decrease the weight, to have like a positive loss. And this is what doing this trick of replacing the square loss with the gradient of the loss, which is like the product for the square loss. It's like it's like a renormalized, but it's like some kind of product between the difference of your prediction and the observation, and the difference of the prediction of expert K minus the observation. If they are on the same side, the loss will be positive, and so the weight will be diminished. It will be will be smaller. And if the prediction, if your prediction and the prediction of the expert are on the other side of the observation, the loss will be negative and it will increase its weight. And this is the idea. And using this loss in the algorithm instead of this loss, you get guarantees that are exactly the same, but with one thing which is important in practice is like until now I told you we are doing like worst case, we are facing adversarial data without assumption. But the issue is like in practice the data is not adversarial. It's not an adversary that we choose the consumption of the customer in France. But there will be some stochasticity, there will be some regularity, some smoothness. And the issue is like if you tune the algorithm to face adversarial data, there will be too pessimistic. There will be too careful with very careful because they will be afraid of something which is weird to happen. And so there are many methods that still can exploit such structure of the data, having like in the worst case they have like the same guarantees as we had before, but if it appears the data is nicer, like if it has some regularity, if it has some assumption, you can adapt to it to have like better rates, better conversion rates. And there are many in the literature, there are many algorithms of these kinds that adapt to this kind of smoothness or of regularity to the data. Like, and I guess Olivier, after me, we spoke more precisely about one of them, Boa. And you see that if you use this kind of method, you get weights that are much more varying because they use the fact that the data is not adversarial and they can be less careless, and you get better you get better performance than what you got with the previous method. And for instance, it's possible to get a better performance if some expert is significantly better than the other one to detect this expert or this model faster. It's possible to get better rates or better performance if there is strong convexity in the loss. Like for instance, I was showing you bounds for the square loss, but I wasn't using the strong convexity of the square loss, and so in practice you can get better rates than what I was showing. And you can get better rates, for instance, if many of the experts are good. Assume like you are combining thousands or millions of models, and 1/3 of them is good. Like if you are combining them, you hope to pay in the log not square root of log of 1 million, but square root of log of 3, because 1/3 of your experts are good. And so there are some ways to have like bounds like this. These are called quantized bounds. And but most of these methods are based on with some well calibration of the learning rate. Like if you learn faster. Another interesting question is what could you do with missing data? So if you have missing data, like assume you have some methods that do not provide prediction at some time, but you still want to combine them. And there is like a trick to use like experts that are not providing prediction at some time. It's just to if some model does not provide any prediction, you replace its prediction by your prediction. So you have like some kind of fixed points to solve, and you get an algorithm which works and which has some nice theoretical guarantees. In the fact that you are comparing your performance with any model when the later did prediction. And this is useful if you want to deal with specialized experts. And this is what I will be talking now. So specialized experts. So until now I have spoken about how to combine experts. But there is another side. Like if all the experts are bad, you get a bad performance. And so another important aspect when you are combining experts or models is to design well the experts that you are combining. And one way to design good experts is to have experts that are sufficiently different from one another. like if all experts are like the same, you most of the time you won't gain anything by combining them. But if all experts are like bring you different information, use different information, then you will get much better performance by combining them to take the advantage of all the different information that are used by the experts. And this is what you see, for instance, in random forest. In random forest, you try to have like very different trees in the forest using like a lot of randomness, because if all the trees were the same, you don't gain anything by taking the average. And one way to have like to build like different experts is to build like experts that are specialized among time for electricity consumption. And this I looked a bit at it during my PhD thesis, doing like experts that were specialized during, for instance, when the weather is really cold or when the weather is like really hot, and using, for instance, only the parts in the data sets to train them when the weather was hot or when the weather was cold, or during summer, during winter, when it's sunny, when it's cloudy, and stuff like that. And so when I was training these models, I was giving more weight to this kind of periods. But the issue is like when I'm combining them, I don't want an expert which is specialized in winter period to produce prediction during summer. And so I was making disabling it, like making not doing any prediction, and then we could use like what I was talking during the previous slide to combine experts that are specialized. And so such specialized experts, they predict only prediction when on the days that corresponds to their scenario. And well, this is what was mainly I should have changed the order of these two slides. And this is what I was talking about like our performance is like some trade-off between the performance of the best experts and what we call the regret, which is the term I was looking at, like the difference between your performance and the performance of the best experts. This is the estimation error that due to the combination methods in square root of log k over t, and this is like the performance of the best experts. And so it's important to improve this term as well. This one you improve it by having better combination algorithm, and this one you improve it by having like better experts. And until now we had only 3 experts. And so during my PhD thesis, I looked at how to enrich this set of experts, and I provided some methods using bagging, specialized experts, or some methods like with some ideas on like bootstrapping, like trying to add new experts that are correcting the error of the experts that are already in the datasets. Like if you see that you have some expert that is always overestimating on some periods, you are trying to build an expert that is underestimating on this period to correct his mistakes. And doing this kind of methods, I went from 3 experts using only these 3 methods to 133 experts. 133 experts, and our performance went from the best of the 3 experts was 744 in RMSE, 0. The best of the 133 experts is 744. So there is no expert which is better, no model which is better than the first 3, which is good because the first 3 were built by IGF and were carefully chosen. But when I combine these 3 experts, I was able to get 625. And when I combine the 100 experts that are specialized, we get a much better performance, because we have like more experts that are different from one another. But what we see is like here we were able to have like a performance which was even better than the best fixed combination. This is not the case anymore when you have many experts, because it's harder to find, you have like in a higher dimensional space, and it's harder to find the best combination. You have more chance of overfitting, and so in practice you have like some trade-off between improving this term. The more experts you have, like the smaller this term will be, but the larger it will be to recover it. And here are like the evolution of the weight of the 133 experts, and they are like they are grouped in colors according to in light blue are the specialized experts that I told you about. In green are the boosting experts. These are the experts that were built to correct the errors made by the previous experts. In orange are like bagging experts, so it's like experts that were built on some random parts of the dataset. We are just using, and in dark blue are the three initial experts. So we see that the weight of the three initial experts is not negligible at all, but we are using the other weights as well.
And what are the others?
Actually, to be honest, I don't remember. This was some
randomized experts.
do you remember?
Yes. You know, we distinguish different ways to estimate the midterm models and shorter correction.
Yeah, you're right. Yeah, when you're using a GAM model, instead you can either fit directly the GAM with like a global GAM model using, like, for instance, the consumption of the previous day as an exogenous variable, or you can use a long-term GAM, which is not using which is just using temperature, the clouds, but which is not using the previous consumption, past values of the consumption, and then using some autoregressive correction, using some autoregressive model to correct the errors. And these are like others are like different variation of the three models using this kind of idea. Yeah, and here are the errors when you were using the exponential weight algorithm I was talking about, and here is when you are using like ML poly, which is one of the algorithms that adapts better to the data than the workplace scenario. Okay, here you see like here are the weights according to the performance according to the number of experts. So we see some kind of like the trade-off between underfitting and overfitting, and this was the gain that we and we see that the overfitting is not that large. You can add many experts without incurring like the curve is quite flat. Here you see the gain that we had, like this was the gain from going to the performance of the best experts, just combining the three experts, and this was the gain that we could get by adding new experts, and which is smaller than what we had by just combining the three first experts, but which is still significant enough, because the better the accuracy you get, the harder it is to improve it. Okay, maybe 2 words about probabilistic prediction. So sometimes you don't want to have like a prediction in average of your consumption, but you want to have like confidence intervals as prediction. And one way to get confidence intervals is by predicting quantiles. By predicting quantiles instead of predicting like the expectation of the electricity consumption. And one way to predict quantiles was to just change the loss function. Instead of using like the square loss, if you use the absolute loss, so you get a prediction of the median of the electricity consumption. And if you move it in one side or the other side, you get what we call the pinball loss, which you can use to predict the quantiles, like the 90% quantiles or the 10% quantiles of the prediction. And once you get prediction of the quantiles, you can build like a confidence interval. And so you can use this kind of ID in the previous algorithm directly, just replacing the square loss with this loss, and we get prediction of quantiles. And this is what some kind of methods that we used a few years ago during the competition, and that was able to, or in part, it was not only this one, but was able to win the competition. And I guess Olivier will talk about that more in details. One important thing is, okay, I told you about the electricity consumption, but during a PhD thesis I tried other data sets, and this kind of combination methods are quite general. Like you can use it for for electricity consumption forecasting, but you can use it for many other applications, like for electricity prices, okay, this is another data set about electricity consumption. You see that it's like American consumption. It's like much higher when the temperature is large because of the air conditioning. And we tried like forecasting of heat load, or we tried other forecasting, and it's always working quite well. So it's like not. And there is another thing which is quite universal, is like the horizon of prediction. Here I was talking about 1 day ahead prediction, but you can look at more longer horizon or smaller horizon. Okay, the smaller is the horizon of prediction, the better this combining methods will be, because they adapt to local changes. But you can use it for several horizons, for instance in hours. So here, like, it's the horizon in hours, and here it's the percentage of improvements over the three models that we had by combining them according to the horizon of prediction. And the larger the horizon of prediction is, the harder it will be for the combination methods to improve the performance of the first models. But you still gain some improvement of percentage.
Is that related to the fact that the conditional mean converges to the unconditional mean with the horizon, and then you don't gain anything in combination when you combine?
I think the reason is like actually I don't really maybe actually I don't really know why. But I think one of the reasons is like this method. One reason that explains these gains of performance is like because every day they get some feedback about it, and they adapt to this feedback, and so it's like it's important to have feedback regularly to improve. If the reason of prediction is too long, you can
It's old.
the feedback is old, and so if you use it, but I'm not sure.
Yeah, one reason for the improvement is clearly the adaptation to with time. So finding the local non-stationarity in the data, conditional to the expert. Because we clearly see sometimes that we do better than the best fixed combination afterward. So how could you explain that? Just because you adapt. But and if you look at larger horizon, it's more difficult to adapt online because the local non-stationality are really short in time. So.
Yeah, so what I'm saying is, suppose you can do it. Suppose you had this adaptation and it works fine. If you increase the horizon, then what you are forecasting is essentially going to be very simple, maybe just the mean of the data. Suppose all you forecast becomes just the mean. In that case, even if it works, maybe you don't have any gain in doing anything. If everything is just the mean.
Yeah, it's the mean, but there is some variance. Like, I mean, if you have like once you are combining experts, if all of them are taking the mean and you are combining them, you are reducing the variance, so you should still gain something. But in our case, we have like some experts which is GAM, which was much better than the other experts, and so it's like maybe when you are going for larger horizons, the difference gets too large. I don't know. But
can I follow up? So is there any skill on the individual forecasters? Is there any skill at forecasting at this longer time horizon? Is there actually skill in the individual expert forecasters? Do they have actually any forecast skill at 2 days horizon, or has the skill that they have, has that sort of decreased down to zero? Is that?
Yeah.
So then combining lots of things with skill zero is not going to give you anything other than.
What do you mean is that some of the experts are really good at forecasting at short term, but not long term. Yeah, that's part of the explanation, maybe. Yeah. Because we have
just one question. Yeah, when you're talking about long term, it's like still 48 hours, so it's still really short term. It's not like 6 months or. These are methods that were built for short term forecasting. So I guess
But I'm just wondering if the skill in individual experts has decreased to effectively zero at that time range, then combining them is essentially still combining a set of skill zero forecast. Therefore, you're going to get no skill.
Okay. One remark is like all of these methods are like coded in some R package, if you want to have a look, and you have like some explanation on my webpage. And I just want to conclude, like, okay, some important things to remember are like, if you combine forecasts, you can greatly improve the performance of Bayes methods. And like in many machine learning challenge, they end up combining different methods or forecast model. One of the issues with the drawbacks with combining forecasts is like then you get some black box algorithm. You don't know which one. Like you have to. It's like a more complicated machinery. And building good experts is important. So sometimes you can find ways to automatically build like hundreds or thousands of experts, and it's important to have like experts that are.
Isn't it even more important than the combination algorithm?
Yeah, I guess once you have a good combination algorithm, most of the combination algorithm will have like similar performance, but it will be important to
have a variety of information.
Yeah, like sometimes if you have a good variety of information and you are just doing like a uniform average, you might have like a good performance. But the good thing with using a combination algorithm is like you can add you can even add like garbage or trash experts that are really bad. It's not that important.
One thing you didn't discuss, I see it's maybe next time, I don't know, but post-processing the experts, for instance, prior to combination.
What kind of post-processing?
For instance, you were telling earlier, maybe you systematically over-predict during some periods, and then you made an expert to systematically under-predict.
Yeah.
But maybe if you had some online, I don't know, a linear regressor to correct for the bias of your experts, then you would have just corrected the bias in the first place, right?
Yeah, but the idea of combination is like it's a way of doing it online. Yeah.
But you can do the post-processing online.
So what do you mean that we could have been more aggressive in terms of the design of experts, like bias?
No, actually, it's a more say theoretical question. Is this interesting to post-process to try to correct your experts, or it's actually better to let your expert be a bit funny, because eventually it helps with the variety of information you have.
Yeah, it's exactly. It's good to have some experts that are, because the issue is like if you are just doing post-processing on the training set, you might overfit or you might. And it's like so sometimes it's good to have like experts that may have like some bias in some way or in some other way, and then doing some combination to have some method which is more robust.
But your question made me think about a situation that can occur that here we have access to the design of the expert. We have access to the algorithm to refit the forecast, but sometimes you just have the forecast without any explanation how they were built in the past, like a meteorological forecast or big physical model forecast. And what you can do is you can just add noise or bias to that, like a random process over that, just to build a variety of experts and doing some online estimation of the bias of the meteorological forecast. So we are currently working on that for pollution forecast. We have expert from pollution, and then we add random walk or that can generate expert.
Because somehow what you say, see, if you have some bad experts, it's almost like you systematically need what's called a de-biaser expert to correct the bias of the first one, right?
For instance, when we were predicting quantile, you can predict quantile. You can even use experts that are not predicting quantiles, that are just predicting the mean. And but if you want to predict the 90% quantile and you only have experts that are predicting the mean, you need something which is predicting larger to correct and you by adding experts that are doing like upper bounds and lower bounds, or adding experts that are predicting two times the experts or 3 times the experts, you can correct this kind of.
But if you can, let's say, train these experts for quantile prediction,
then I guess it should be better.
But in practice, it's right. For example, I had a recent master thesis which heavily worked with this Opera package, which was combining wind power forecast from German utility, and they are just interested in the median, because their traders just can for some reason deal with medians. not for something else, but they are buying also quantile forecast for other quantiles and so on. So what we did actually was basically what you said. So we trained for the median, but plugged in all the other forecasts they got for the 90% quantile and so on. And they heavily improved the forecast, even though they are not predicting the 50%, but 90% or 10%. But if you do so, it's often not the best to, at least what we noticed, to go for the convex combination. Because this is quite a small range you're looking at. If you have some which are highly above or below, then it's something good to assign to these experts, which are not, say, targeting the right thing, to assign negative weights to them, and then to go to a larger space for your parameters. Which of course you could take the full linear space, but usually this gives you, it's crazy large, and you're getting too high variation in your weights. But for example, we found that if we use affine combinations, so just the sum equal to 1, but allow negative weights, worked quite well for us in these kind of things. So in general, I think restricting the parameter space between the very strict convex thing and the large linear thing to some extent seems to be, in these kind of situations, a suitable thing to do.
Just one remark about this, which you may think about that remark. When you are building the experts, what is important is to have experts that use different information. For instance, this light blue experts was not really good if you looked at just the performance, and the reason was it is not using at all meteorological information or meteorological prediction of the next day. It's just based on the past consumption and using similarities of the consumption of this day to the similarity of the next day. And so, but since it is not using at all the prediction of the temperature to make the prediction of the consumption, if there is an issue with the prediction of the temperature, it will be the only one, not to having like some problem with it. And this is why even if this prediction in average is worse than the other one, it will bring like some important new information in some kinds. And especially it's during the winter period.
So if I could maybe come in with two slightly different questions. So if you go back to the bounds that you had early on.
To which one?
Very early on. Yeah, that one.
This one?
Yeah. I mean, what assumptions are underlying that? I probably missed it, but what assumptions are you making on the form of the data?
No assumption on the form of the data.
None whatsoever to get those bounds.
It's bounded by DB. It's the only assumption.
There's no distributional assumptions whatsoever?
No distribution assumption.
Completely free?
Completely free.
Okay.
It can even, you can imagine some adversary, and at each time step, the adversary know your prediction, know the past, your past prediction, know everything, and decide according to your prediction everything. So it's like with some adaptive adversary. And you get this kind of bound, it's just deterministic bound on real numbers.
Okay. But the bound is quite a hard restriction, so you have all the moments and. So
The idea is like, but the data is bounded, so it's like the same as having like.
And then I'm just thinking about the weather that we're experiencing at the minute. So you say you may have some models that have got experts that are better at winter than others. But if you have days like we had yesterday in February, which are anomalous days, where it was 22 degrees, so clearly the demands on the energy are going to be quite different in winter because it's more like a summer day. How does it deal with that anomalous structure? So in that case, you want to have some summer raters in the middle of winter, right? Because you get this anomalous structure.
To assign the weights, we didn't use at all any additional information. We are not.
No. But I'm just thinking in general.
I'm
just thinking in general. You get these sort of wildcard periods in the data. So yeah, if the data has a steady-ish state to it, to have experts that are more wintry and others that are more summery makes a lot of sense. But actually, you do have anomalous periods, and so you have to.
It's like holidays in France. I think you removed in your data set.
Yeah, in this data set I removed special days like maybe for.
So I think your method is very generic. very nice, but for EDF, I would say, or RTE, what you want to focus on are on those atypical days where you will be bad at predicting, forecasting. And so I guess.
But I guess it could work for this as well. The issue is like the theoretical performance is like some average, and so it's like these days will be hidden in the other days, because okay, if you use this even for atypical days, you will just get some more robust method, more like a method with which will be some average of many methods, and so it will be more robust. But what the issue is like our experts, our models were not built for these atypical days, so it didn't make any sense.
So that's what I'm thinking is, so where could it go to allow for that atypical behaviour?
I think one solution, something we looked recently also, is when you do some bagging, we show that it really it gives you the diversity of the experts, relative to the distribution of the data, and you can imagine if you have a data set with let's say 5 winters, 2 among them are special winters like this one. You can just bag according to block bagging your data according to this and have some data set with more special winter and just fit an expert and let the aggregation choose in real time what is the specificity of the winter you are going on right now. So and we experience that the most important thing in this bagging design expert is to find the good way to bag your data. So it's like finding the most important periodicity of the data, the local stationarity, etc., and bag according to that. Which it works well. Yeah.
I think your framework is very good on one side for tapping things, and maybe not the best for other things. If you have the data, the information, like RT or EDF to forecast the electrical load. There might be models like neural networks that are already ensembles. So
yeah,
we tried it and they do better than random forest or things like that. So you should look at that for getting a lower bound. But where I see the power of your method is, as you said, if you're buying to some vendors some models, and they might have different data they're building. They're using to build their models or different information. There, your method is really interesting.
No,
so I guess it's like the pollution.
The other thing with random forest is like you can include it into the exports, and the issue like with the drawback of neural networks is like it's really heavy to optimize, and you cannot optimize deep neural networks every hour or every day or something like that. Well, you can have like many different neural networks or deep learning nets there, and many methods, and you just optimize the way you combine them, and so you get some adaptation to time over time without having like some calibration to.
We did it every month, and we included the atypical days, and it worked pretty well. So
yeah, but
for sure, it's maybe
you can do it every day or every hour.
Yeah, no, I can see an advantage here. But I think in your models, you should look at neural networks just to have a baseline at some point.
Yeah, but I'm not sure neural networks will provide a lower bound.
Yeah, no, not always, but as I said, we did it.
Okay. Yeah. Just to make sure, you gave a number which is the best combination.
Yeah.
So that was the best convex combination.
Yeah. Yeah, that was. If you can look at the best linear combination. Okay, with 3 experts, it's roughly the same because all experts are unbiased, so the combination is the right one. But with the 133 experts, as told, it's sometimes better to assign negative weights to some of the experts and larger weights to some other, and the best linear combination is better. And so then you can use other methods.
But the number that you gave was the convex.
Yeah, all of these numbers are for convex combination.
Maybe the last question before the break.
So, it's a slightly different setup. So one of the problems I often come across is the combination of weather forecasts maybe applying to power, but the combination plan forecast. So let's say I have 3 forecast systems, each of which is an ensemble forecast, produces 50 members. So I've got 3 expert systems, but each are providing 50 expert estimates.
Okay.
What's the way you would see of combining that information to produce a forecast? So, particularly if I want a probabilistic forecast at the end of it, in this kind of world, would the route be to treat that as 150 separate experts, or 3 experts? I take the ensemble mean in each case, and then combine the ensemble
either
mean.
use some hierarchical structure to do the prediction, either you have like some flat combination with the 150 experts. Actually, I don't know.
No, in that case, what you do is, what's the product you want at the end? If it's a probabilistic forecast, you're just going to use all these guys to make a prediction for the condition of expectation, and then for some of the quantas, right? You see what I mean?
Yeah. Yeah.
So, as you were showing here, it's just you're going to use all these guys as inputs.
But then you're just training for the marginals.
Yeah, that's what I said. Depends on the product you want.
But
If it's for the marginals, it's straightforward. If you want something else, it might be.
So-
Yeah,
But I
that's
think-
fine.
but I guess the-
Yeah, otherwise you just put them together and that's it. And you have 150.
But as I said, you were allocating weights that kind of persisted in time in some sense.
Yeah.
And my individual ensemble members have no meaning from one time to the next. So ensemble member 1 from one time point does not correspond to
She
ensemble
thought
1
about
to
that
the next
question.
time set.
Yeah, the issue with ensemble forecast exactly, you cannot.
You have to sort. You have to
Yes,
sort.
because
Yeah.
the-
And
Okay.
I don't remember what, but I know someone who thought about that, but I don't remember what was his solution. If he decided to sort the experts by the decreasing order or increasing order, and assign always number 1 to the expert, which is the larger one, and I don't remember what was the solution he
Yeah,
decided.
you have to design a convex space, which is order in a way.
Yeah.
So do a transformation of a tag of your expert according to I don't know order relationships you can build on your dataset.
Can maybe one of you guys explain this to me at a coffee
Right.
break? Because
Maybe you can, because I don't remember what she did.